video, we will be explaining and demonstrating how to use the Big Five. So what is the Big Five? Well, they're a set of 5 equations that will help you in solving motion problems. In order for these equations to provide accurate and realistic results, they must be applied to motion with constant acceleration. All of these equations, which were derived from a velocity time graph, help determine one of the following kinematic quantities. First, there is initial velocity, which is the velocity the object starts with. Then there is final velocity, the velocity the object ends with. There is also displacement, which is the final position subtracted from the initial position. Acceleration, the rate at which an object changes its velocity in a specific time interval, which is the change in velocity over the change in time. And finally, delta t, which is the final time subtracted from the initial time, or the total change in time. In each of these equations, there are 4 related kinematic quantities. This means that in order to determine one kinematic quantity using an equation, you must be given at least 3 given quantities. These are the 5 of the Big Five equations. As you can see, each of the 5 come with 4 given kinematic quantities in the formula. Let's take the first one for example. The equation consists of final velocity, initial velocity, acceleration, and the change in time. Whenever a problem provides any 3 of these kinematic quantities, you will be able to find the 4th unknown using simple algebra to isolate for that desired unknown. This applies for the rest of the 5 equations. Let's do an example problem. A car is traveling 137 kilometers per hour when they see a cop in an area where the speed limit is 100 kilometers per hour. The car can accelerate at a rate of 5.4 meters per second. What is the minimum time in which you can get your car under the speed limit? Here we've decided to specify the moment the driver sees the cop as the origin, which is when the car begins to slow down, making it event 1. Event 2 is when the car has slowed down to the speed limit. This shows a positive displacement. We fill in our 3 given kinematic quantities directly from the question and state that we must find time in seconds. We must firstly convert initial velocity and final velocity to meters per second. This is because acceleration is given to us in units of meters per second squared, and time is desired in a unit of seconds. For demonstration purposes, we showed our calculations for conversion separate from our pictorial representation, but a correct practice is to convert the units directly on the pictorial representation. Don't forget your units. Here is our physics representation. Our motion diagram shows positive displacement. The increasing interval of space between the dots shows that velocity increases from event 1 to event 2. Our velocity vectors also show positive displacement, and that the velocity at event 1 is greater than the velocity at event 2. Our displacement graph shows positive displacement that decreases as time goes on. Our velocity graph shows a positive velocity that is decreasing, and our acceleration graph shows a constant negative acceleration. We know this makes sense because the act of slowing down is represented when the sign of velocity and acceleration are the opposite. Here is our mathematical representation. We first state that we must find the change in time to solve this problem. We can use the first of the Big Five equations because final velocity, initial velocity, and acceleration are given, and change in time is unknown. We start by rearranging the formula so that change in time is alone on the left side, so it is clear that it's being solved for. Then we simply plug in our given values using proper units and sign conventions. We found that change in time is about 1.98 seconds, but because negative 5.2 meters per second squared has the lowest number of significant digits in the problem, we state our final answer as 2.0 seconds. Therefore, the car takes a minimum of 2.0 seconds to slow down to the speed limit. Don't forget your punctuation. In conclusion, here are a few important things to remember while working with the Big Five equations. You must use proper sign conventions. Remember that when the signs of acceleration and velocity are different, the object is slowing down, versus when their signs are the same, the object is speeding up. Also, you must be provided at least 3 given kinematic quantities. But most importantly, remember that these 5 equations only apply for problems with uniformly accelerated motion. We hope you learned something from our lesson today. Thanks for watching.